Good morning. My name is Leah Valentine, and I'll be presenting mine and my partner Angela Ponceno's research on how microbial and mycorrhizal additives affect the growth of Salvia, rosmarinus, and Mars regolith. The purpose of this research is to try and find ways to sustain plant life on Mars in the most sustainable, economic, and feasible way. The regolith simulant we are using, Mojave Mars simulant, or MMS2, emulates the chemical composition of the regolith that naturally occurs on the surface of Mars. Previous experiments with growing plants directly in this simulant showed little success in supporting plant growth. In addition to the compact clay-like nature of Mars regolith, it's also deficient in inorganic or organic forms of nitrogen and carbon, two of the most vital elements for plant growth. On Earth, nitrogen is mineralized, fixated, denitrified, and distributed throughout the ecosystem through the nitrogen cycle. The lack of this cycle on Mars will inhibit any plant growth from occurring unless artificially introduced. Rather than solely adding unsustainable nitrogenous-based fertilizers to supply nitrogen to our plants, we wanted to try and recreate the ecology of a healthy earth rhizome microbiome. We hypothesized that the addition of mycorrhizal fungi and beneficial soil microorganisms would promote plant success in Mars regolith. Healthy earth rhizospheres, or root zones, contain numerous species of mutualistic microorganisms and fungi, both of which can communicate with the plant to improve plant health. Mycorrhizal fungi form a mutual symbiotic relationship with plants and facilitate nutrient uptake and encourage root development and growth. Plant growth promoting rhizobacteria also interact symbiotically with plants and play a critical role in nutrient uptake by fixing nitrogen into forms that can be utilized by the plants, as well as improving water use efficiency, fighting against plant pathogens, and assisting the plant in adapting to harsh environmental conditions. Once introduced to the rhizosphere, the rhizobacteria quickly anchor themselves to root hairs, aggregate on root tips, and colonize inter- and extracellular spaces. Our plan was to inoculate the rhizosphere plants in Mars regolith with a diluted blend of nitrogen-fixing, phosphate-solubilizing, and saprophytic microorganisms. We chose to use Environoc 401 from Biodyne. It's a consortium of microorganisms that's utilized in commercial row crop farming in nutrient-depleted and degraded fields in the Midwest United States. It has promoted more productive crop yields, soil health, and plant quality. These microbes are bottled in a vegetative state and can synthesize endospores so that they can persist in adverse environmental conditions with low nutrient availability until they're inoculated. This microbial blend can be lyophilized or freeze-dried into a pellet and shipped along with highly concentrated micronutrients, making it ideal for space travel. These rhizobia species also specialize in decomposing organic matter, plant hormone production, enzyme secretion, denitrification, and assisted uptake of nutrients like phosphorus, iron, carbon, and nitrogen. When I joined this research group in spring of 2020, the focus was on altering the physical composition of the Mars regolith to better support plant life. These experiments resulted with the composition that we currently use, a 2-to-1 ratio of Mars regolith to Cedar Grove earth compost mix, which has had success in supporting plant life. In summer 2020, we introduced mycorrhiza concentrate and rhizobacterium to our experiment. All rosemary seeds that were sown in regolith failed to germinate, so for the second experiment in autumn, we took cuttings from a mother rosemary plant, treated them with an IBA rooting hormone, and transplanted them into pots with and without treatments. Each cutting I transplanted had difficulty establishing and did not survive in the Mars control. My only plants that were successfully propagated were my earth control, microbe treated, and mycorrhiza in microbe treated pots. My research partner Angela had success in her mycorrhiza and microbe treatment and Mars control, and her most successful cutting was the one that was grown in her mycorrhiza treated pot. Though our results varied, they were still very encouraging and suggested that there were beneficial interactions between the plants and these additives. We chose rosemary as our focal plant for the third and final experiment in this series of experiments because it is cold and drought tolerant, has exhibited resilience to harsh media in past experiments, has been observed to interact positively with rhizobacterium, and is capable of symbiosis with both endo and ectomycorrhiza species. We decided to perform two identical 100-day experiments on rosemary, mine experiment A and my research partner Angela's experiment B. We used large plastic tubs to simulate a greenhouse with LED lights fixed to the lids. To provide nutrients for the microbes, we did a soil soak of organic fish fertilizer composed of nitrogen, phosphorus, and potassium. Since we've had trouble germinating seeds sown in Mars regolith and had varying success with vegetative propagation, we decided to sprout the seeds in water and then transfer to pots to confirm seed viability. We planted 5 rosemary seeds in each pot and recorded plant and leaf growth, as well as took observations of plant appearance, regolith moisture levels, mold growth, and root development. We observed rosemary growth in 5 different clear plastic pots: earth control, Mars control, regolith treated with microbes, regolith treated with mycorrhizal concentrate, and regolith that had both treatments. To improve moisture retention, porosity, and drainage, we also added a half cup of vermiculite to each pot. We anticipated that the rosemary would grow the best in 100% earth soil and would have difficulty growing in 100% Martian regolith. We predicted improved growth success in regolith pots treated with mycorrhizal concentrate and biodine when compared to untreated regolith. On day 100, plants were pulled out of pots and measurements of leaf count, root length, total plant length, and stem length above the soil line were taken. In each pot, there was at least 1 or 2 plants that surpassed their neighboring plants in growth. 2 of the 5 microbe-treated plants were very successful, while the other 3 were short, had few leaves, and little root development. We speculate that this could either be from competition for root space and soil nutrients, or it suggests that the 3 stunted plants were not successfully inoculated with rhizobacteria, while the 2 tall plants were. The equipment that we needed to determine successful inoculation was inaccessible for this experiment, however. As anticipated, the earth control had the longest roots with the largest volume and the tallest plants with the most leaves. Plants in earth control had a high surface area of branched roots and longer, thicker stems and taproots. The second most successful plant, with the most earth-like root structure, were grown in the pot treated with microorganisms. The 2 most successful plants treated with microbes had long, thick, branching root systems with high surface area. The 1 plant that survived in the pot treated with mycorrhiza had short, branching roots, and we predict that the limited growth could be due to the difficulty for the plant to acquire nutrients from the regolith, or the inability of the roots to move throughout the substrate. The pot with both fungus and microbial treatments had good root branching, generally longer roots, thicker taproots than the plants only treated with microbes, but the taproots and stems were still not as thick as the earth control. For experiment A, 3 rounds of plantings occurred for the Mars control, with a total of 12 sprouts planted. All of them failed to establish and survive, so the Mars control success rate for experiment A was 0%. Experiment B had 2 out of 4 plants survive, giving us an average success rate of 13%. We had a relatively low average earth control survival rate at 67%, likely due to the soil not being kept sufficiently moist during the rooting period. More frequent waterings of the earth soil compared with Mars regolith were observed to be imperative to support plant growth. This suggests either more water holding capacity of regolith over earth or more drought tolerance in plants that were grown in regolith. Experiment A's mycorrhizal treatment had a 13% success with 1 out of 8 plants surviving. Together, we only had 2 out of 13 plants survive in this treatment, giving us an average 15% success. The highest survival rate for both experiments was observed in the regolith treated with microorganisms, with 84% success in experiment A and a combined success rate of 70%. Pots with both treatments had mixed results between experiments, A having greater success than B, and a 33% average survival rate between the 2 of us. The plants grown in pots treated with microbes and those with both treatments had very similar average results, though the plants with both treatments had slightly longer roots and total plant lengths. For experiment A, there was only 1 survivor in the mycorrhiza treatment, and growth was stunted both above and below the soil line. This plant had negligible growth, and plant growth plateaued after the 4th week, though it did remain alive until the end of the experiment. There were no results for the Mars control because there were no survivors for experiment A. Results varied between experiments A and B, but both experiments observed benefits of adding mycorrhiza and rhizobia. It's extremely difficult to get rosemary sprouts to establish in Mars regolith, but it appears that successful inoculation of rhizobacteria did promote root development and plant growth. Although the establishment success of plants in mycorrhiza treatment were quite low for both experiments, it appears that they do promote root growth in pots that have also been treated with microbes. For future research, we would like to explore nutrient recycling after plant harvest and incorporate decomposer specialist microorganisms in addition to our rhizobacterium. We also plan to experiment with different crops, increase our test subject count, and establish a controlled environment such as a greenhouse or a glove box. Further research would benefit from the ability to confirm inoculation, as well as explore how siderophores interact with ferric oxide. We plan to continue to collaborate with Biodyne and experiment with their other teams of microorganisms as well. Thank you so much, everybody, for your interest and attention.